Welcome to the Science, Microbes, and Health podcast, covering emerging topics and challenges in the fields of probiotics, prebiotics, synbiotics, postbiotics, and fermented foods. This is the podcast of the International Scientific Association for Probiotics and Prebiotics, known as ISAPP, a nonprofit scientific organization dedicated to advancing the science of these fields. Check us out at www.isappscience.org. I'm Dr. Mary Ellen Sanders, ISAPP's Executive Science Officer. I hope you enjoy this episode with your hosts from the ISAPP Board of Directors, Professor Colin Hill and Professor Dan Tancredi.
Hello, everybody. My name's Colin Hill.
And I'm Dan Tancredi.
And our guest today, I'm delighted to say, is one of our more recent board members, Kristin Verbeke from the University of Leuven in Belgium. You work in the gastroenterology department, but you're not a clinician, you're not a gastroenterologist. Can you explain how that came about, how you came to work in a gastroenterology department?
Okay, thank you very much. Hello to everybody. By training, I'm actually a pharmacist, and I did a PhD and quite a long postdoc period in the laboratory of radiopharmaceutical chemistry. So there I worked with radioactive isotopes and tracers that are produced and used in the nuclear medicine department. But then at a certain time, they needed someone in our hospital to do the breath testing in the hospital, to be responsible. So the breath testing, these are functional tests for upper gastrointestinal processes to measure those. And you use normally stable isotope labeled tracers. And then you can measure, for instance, processes like digestion of lactose, of carbohydrates, of protein, of fats, also gastric emptying rates, Helicobacter pylori in the stomach, that kind of things. So that's how I got involved in the world of gastroenterology. And as we had almost for all proximal gastrointestinal parameters a test, we shifted and tried to analyze what happens in the large intestine and see if we could measure there also what happens and how it works. And then, well, if you measure something, you need to know if you modulate, if you change the processes, can you still measure it? And that's how then I got involved with pre and probiotics, because initially we just used those pre and probiotics to modulate the bacterial metabolism and to see whether we could measure the effects on the metabolism.
So, Krista, when would a patient or a healthy individual want to have a breath test done? What kind of diseases would it be an indication of, or what would you be looking for?
Well, the most of our breath tests are lactose intolerance tests. So these are patients that suspect lactose intolerance or lactose malabsorption. And then we also have gastric emptying tests. That's often patients with diabetic gastroparesis that want to see if they have a delayed gastric emptying, that might have an effect on the timing when they have to inject their insulin to better time it versus the glucose response that they expect after the meal. And then we also have many patients that need Helicobacter pylori tests, that kind of things. It is very divergent. It's always gastroenterology patients, but the indication can be very diverse.
And Kristin, I find interesting that you've done a lot of work on characterizing the colonic metabolism of the microbiota, but not just the fermentation of carbohydrates, but also proteins. Can you talk a little bit about that, like protein fermentation, and is that indicative of bad diet or poor health, and the implications of that?
Okay, so the majority of protein that you eat is digested in the small intestine, but it is not all digested. And we expect that about 5% of animal protein is not digested and ends up in the large intestine, where it gets fermented by the microbiota. Plant-based proteins are a bit less digestible, so there it can be 10-15% that ends up with the microbiota. And if the microbiota ferments protein, we get the production of a number of metabolites, like ammonia, phenolic compounds like paraclysal, phenol, indole, derivatives of indole. And we think that those metabolites can be toxic for the large intestine, but also for our overall health. But that is very difficult. I mean, that has been shown difficult to prove. When you do in vitro studies and you bring those compounds in contact with colonocytes, for instance, you see toxic effects. So intrinsically, these components are toxic. And then also the fact that protein fermentation occurs mainly in the distal colon, and that most of the colonic diseases, like for instance, colon cancer or ulcerative colitis, occur also in the distal colon, have generated a hypothesis that the fermentation metabolites might induce those diseases. But this has never been proven. And we have done a study but it was in healthy participants some years ago, where we gave them a high protein or a low protein diet. And we indeed saw differences in protein fermentation, but there was no difference in the cytotoxicity and the genotoxicity of the fecal water. So we concluded from that within the whole fecal matter that contains so much different compounds, the protein fermentation metabolites are not the ones that are responsible for the main toxicity.
I guess, Kristin, you might expect if it was, that there'd be some almost epidemiological evidence that, people who are big into fitness and eat very high protein diets and bodybuilding and things, that they would have more problems then with the distal intestine. But is there any such evidence? Or are you aware of it?
I'm not aware of that. I did not specifically look at that neither, but after this first study in healthy participants, we did a new study that's quite recently in patients that underwent bariatric surgery. Because in those patients, at least the ones that have a Roux-en-Y gastric bypass, we think about, it's not only thinking, we also could show it that the protein digestion is reduced. And so they have a larger spillover of the proteins into the colon, more protein fermentation, and we see there also more cytotoxicity of the fecal water, even up to 1 year of surgery. What we had not expected was that in the participants that got a sleeve gastrectomy, where we just reduce the volume of the stomach and do not do a nutrient-free routing, we also saw more protein fermentation. And so we think that also the transit may play a role, because both the types of patients suffer from constipation. And if you have a slow transit, you can also have increased protein fermentation, because then there is more time for the bacteria to ferment the proteins. For the Roux-en-Y gastric bypass, you have a much more profound anatomical rearrangement, whereas the sleeve gastrectomy is more just a reduction of the capacity to eat, but you do not change the small intestine.
Kristin, one of the things I admire about your work is that we all as scientists have expectations about what should happen, but actually proving it is quite challenging. So we have expectations that the metabolites from the short-chain fatty acids are beneficial for health, but, developing that mechanistic evidence is a challenge. Can you talk about some of the innovative ways that you've had to try to target the delivery of short-chain fatty acids to get a better idea of mechanism and implications?
And maybe, Kristin, you could start by just telling us what short-chain fatty acids are and how they normally arrive in the gut.
Okay, so short-chain fatty acids are just short acids. Normally, in the context of the gut and colon fermentation, the main short-chain fatty acids are acetate, propionate, and butyrate. So molecules with 2, 3, or 4 carbon atoms. Very simple molecules, very small molecules. But they are the main anions in our large intestine, and they are mainly produced from fermentation of dietary fiber. So when you eat fibers, fiber are not digested by the mammalian enzymes. And so they end up in the colon with the bacteria, and the bacteria ferment them, and those acids are their main metabolites. And we think that they are responsible for many of the health benefits of eating fiber. But that is difficult to prove, and that has to do with the specific kinetics of these short-chain fatty acids. And so the fact is, when they are produced in the large intestine, they are very efficiently and quickly absorbed. So what you measure in fecal samples is only 5%, 10%, which is what we estimate, and of actually what has been produced and not been used. So it is the leftovers. But when they are absorbed by the colonocytes, they're immediately used there and oxidized because they serve as a kind of energy source for these cells. And then they go via the portal circulation to the liver, and then they are used again for some metabolic reactions, and only the leftovers come into the systemic circulation. So for a long time, people have measured short-chain fatty acids in fishes, but I don't think this is the most relevant part because it does not adequately reflect what has been produced. And that was because it was difficult to measure them in plasma because of the very low concentrations and because, you have to be careful for contaminations. Acetate is everywhere in our environment, and you have to be very careful not to have contaminations. But nowadays, it is feasible to measure short-chain fatty acids in plasma. So their kinetics make it difficult to measure them and to know how much actually is produced in the colon. And if you don't know how much is produced, it's of course also difficult to know what their effect is. And if you can administer fibers to people and see that there are short-chain fatty acids and that they get into the systemic circulation, but it is always difficult to prove that they are the cause of the modulating factors of an effect if you don't know how much it was. And so we thought we need to administer known amounts of those short-chain fatty acids into the colon of the people so that we can see what happens after that. And in the first study, we just wanted to know how much of what we administer gets into the systemic circulation. And for that purpose, we used, again, stable isotopes, because that is what we are good at. And we put them in capsules, and we did a coating around the capsules that only dissolves when they arrive in the large intestine. So we did some in vitro and in vivo validations that the capsules performed well. And in that way, we could measure in the systemic circulation only those short-chain fatty acids that originate from the colon, because it was only those ones that were labeled. And so we could quantify the amount of, for instance, acetate that arrived in systemic circulation, which was on average 36%, but there was quite some variability in that. The amount of propionate was only 9%, and we only found 2% of butyrate, 2% of what we administered. And that was more or less in the range of what we expected, but in this way we could really measure it. And then we did, in a second step, we, instead of using tracer amounts of the short-chain fatty acids, we used physiological doses, a dose that corresponded more or less to 20 grams of fermentable fiber. And we gave that to participants, and we looked at the effect on gut-brain communication, and we chose stress as an outcome parameter. And in that way, we could show that we had male participants that we subjected in the lab to a stress test, and we measured their cortisol response to the stress. And after they ate those capsules for a week, they had active capsules or placebo capsules. We did the stress task again, and then we could show that the ones that had the short-chain fatty acids had a lower cortisol response, so a lower response to stress than the ones that had the placebo capsules. And we also saw a correlation between the change in cortisol response and the increase in short-chain fatty acid concentrations in plasma. So the more the short-chain fatty acids increased in plasma, the more the cortisol response decreased, which is an additional argument to think that the short-chain fatty acids mediate this effect. And so we are now doing follow-up studies to see how short-chain fatty acids can reduce cortisol response. So we try to further elucidate these mechanisms, and we plan to do PET imaging in the brain of those participants to see if, for instance, the short-chain fatty acids inhibit also the HiDAC enzymes, and if that could be the mechanism by which they affect the cortisol response. But these are ongoing studies, so we hope we can find out more about the real mechanisms of how it works.
It's exciting work because, you wrote this terrific review paper on the role of the short-chain fatty acids in modulating those gut-brain interactions. But we really don't know too much about that. And now you're kind of investigating that. You've said in some of your work that this same technology can be used for other kind of interactions between the gut and other organs. Are there any on the horizon that you're envisioning? Any like gut, lung, or any other kind of?
I'm now thinking mainly about gut liver, because the liver is the first organ that the short-chain fatty acids encounter when they were absorbed. And I think that if you look at the mechanisms of fat oxidation, for instance, short-chain fatty acids might also affect the fat oxidation and the fat synthesis in the liver. And that is one of our next projects that we would like to do, is to investigate if we can also see that they really have an effect there and have an effect on lipid metabolism. Because now people with NAFLD, for instance, patients with NAFLD, there is no treatment. They are already advised to eat less fat and to have a better, more physical activity, but there is no real medications. There are pharmaceutical compounds in development, but so far they have not been approved. And I think eating less fat is fine, but maybe we should also get better results with increasing more fiber or combining both and working on two fronts rather than only reducing the fat intake.
And NAFLD, you mentioned, that's non-alcoholic fatty liver disease.
It seems that nowadays up to 1/4 of the people in industrialized countries suffers from it when getting older. So it is something that is important. And the first stage is NAFLD, so the fatty liver actually, but then the disease can develop into steatosis and eventually into hepatic cancer. So it is important to prevent the progression, and if it would be possible to avoid the disease. And I think if we can contribute with short-chain fatty acids, why not? It would be nice. And of course, we can always advise people to eat more fiber, but eventually you could also think of developing capsules with short-chain fatty acids as a treatment if it would work.
Do you think the short-chain fatty acids could be administered, intravenously or like bypass the gut completely and deliver them directly into the bloodstream? Or do you think that might be a step too far?
It is, you can do it. It is possible, but the half-life of short-chain fatty acids in the plasma is very short. So they come into the blood and they go out. We see that also if we do a dietary intervention, for instance, also with the capsules that we have, it's not a slow release. So they release their content, your concentrations of short-chain fatty acids go up and go down. And within a few hours, they have gone again. We have done studies with a fermentable fiber, where you can see that the plasma concentrations go up and stay at, it took about 8 hours to have them reduced back to baseline. I think that to have a more sustained increase in short-chain fatty acids, that you would need fermentable fibers 3 times a day, something like that. Because otherwise, if you inject them, they will very quickly disappear from the plasma.
And your work is really exciting because it gives a mechanistic, a molecular basis to the prebiotic effect, or at least one of the effects that prebiotics might have. Do you think that it could at all be a part of the probiotic health effects? I mean, some probiotics are obviously metabolically capable of producing short-chain fatty acids. Do you think that they could metabolize and produce enough in the gut to have some of these effects as well?
I think you need the combination of the bacteria that produce the short-chain fatty acids, that are able to do it, that are saccharolytic, that prefer to ferment carbohydrates. But you will always have, I think you always have to provide substrates also to the bacteria, because if they do not have a carbohydrate, they cannot produce short-chain fatty acids. So I think you need the combination of having prebiotics and the right bacteria is the optimal thing, I would say.
You're talking there about synbiotic, potentially, the combination of prebiotic and a probiotic. Yeah, that's very exciting. At the other end of the gut, you talked earlier on about lactose intolerance and probiotics and have been shown to have some kind of effect there. Do you think that's just simply, again, the metabolic activity of the probiotics on the lactose high up in the gut, or have you done any work in that area?
We haven't done any specific work, but if you add probiotics for lactose intolerance, I think the main aim is to the probiotics already digest the lactose that is in the product, so that it does not that it gets absorbed and it does not induce any effect. What we do see is that some of the people that are clearly lactose intolerant, that have lactose malabsorption, that I have to say it like that, are often or sometimes not lactose intolerant. So it means they do not have any complaints, although it is clear that they do not digest the lactose. And in those people, lactose actually works as a prebiotic, and it may stimulate the good bacteria, or it may stimulate bacteria that do not produce a lot of gas, for instance, and which can explain why they are not intolerant.
Where do you think this research is going? What do you think it's going to lead to? You kind of maybe hinted at a couple of possibilities that people with particular conditions or in a preventative way might take capsules of short-chain fatty acids, or do you really think that the dietary intervention, the fiber intervention, is always going to be a better intervention for some of the reasons you gave earlier?
I think for me personally, I think it convinces me to eat more fiber and to eat different types of fiber and fermentable fiber. Try to eat fermentable fiber, and I think you cannot eat enough, or you cannot eat too much of it. So for me, the more I see that short-chain fatty acids really do something, the more I'm convinced to eat more fiber. Yeah, some people, I think it's not easy to eat more fiber. I can imagine that there are conditions where you cannot eat a lot of fiber, and for them, it might be an option to develop short-chain fatty acid capsules if that would give them the same results.
And in very practical terms, when you say you choose to eat a lot of fiber, what vegetables or what materials are you actually eating to give yourself all that fiber?
I eat a lot of fruits, really a lot of fruits, and vegetables. I think all kinds, all colors. I really eat a lot of vegetables and a lot of fruits, and also cereals. Wholemeal cereals. I like a lot all the types of muesli and things, and oats.
Kristin, this question's going to be a little bit out of left field, but I can't help but wonder, somebody with your expertise in characterizing what happens in the colon, and also as a pharmacist with a PhD, is the field of coding, like pharmaceutical coding of either the acids themselves or the probiotics and prebiotics, is there a lot of active research into how better to make these capsules so that they get to the colon or get to where they need to be? Or is that pretty much off the shelf? Everybody knows how to do it, and it's pretty standard.
Well, there are a few options. You can have colon delivery either by time-dependent coatings, by pH-dependent coatings, or by bacteria-dependent coatings. The coating that we used was pH-dependent. It's not that straightforward to have, and it's expensive. So we have now found a company that wants to coat our capsules in GMP conditions so that we can also use them in patients' trials. We are now also starting a trial in patients, but it is really expensive. So we have to combine all our studies where we want to use the capsules, and then combine all our budgets and make the capsules in one batch, because it is produced on an industrial scale. So that means that a bigger batch does not increase the cost too much. It's really initiating a production that is very expensive at the moment. There are efforts to pre-coat capsules that will be available. It will make our life easier in the sense that then you can buy the coated capsules and fill them and close them, and then that's done, and that's it will be much less expensive, I guess. But the ones that we tested recently are dissolved already at pH 6, which is too low. It has to be 7. But the company was working on that to also have capsules that dissolve at pH 7.
Okay, I'm glad to hear it's active. It's still an active area where there's room for improvement.
It's really fascinating work you're doing, Kristin, and we're so glad that you're joining us on the board of ISAPP to bring this kind of level of expertise, because I think it's something very new to us and a fantastic area of research. So thank you, and thank you for taking the time today to chat.
Thank you, Kristin.
Okay.